the Sun. From Earth, it appears as a calm, shining disk in the sky. In reality, it's a gigantic thermonuclear reactor, 1.4 million kilometers wide, generating more energy in a single second than humanity would use in a million years. The Sun is the source of all life on Earth, but also the driver of cosmic storms that can knock out satellites, disrupt communication, and endanger astronauts. For decades, humanity had never sent a probe closer to the Sun than the orbit of Mercury. That changed in 2018, when a small but incredibly robust spacecraft launched from Cape Canaveral, the Parker Solar Probe, a mission built to touch the Sun. This video dives into why this mission is unique, the extreme challenges it has overcome, the records it's breaking, and how it's reshaping our knowledge of the universe. Get ready for a story future generations of scientists will study. The Sun, both hell and the cradle of life. The Sun is not just an ordinary star. It's a G2V yellow dwarf, a thermonuclear furnace that converts about 600 million tons of hydrogen every second. Its gravity holds the solar system together, but it's also the source of unpredictable space weather. Every second, the Sun emits more energy than all of humanity will ever consume. Solar eruptions can destroy satellites, knock out power on Earth, and pose a hazard to astronauts. But despite dozens of observatories watching from afar, our understanding of the Sun, especially its mysterious corona, was limited. The corona, the Sun's outer atmosphere, can reach millions of degrees, while the surface, the photosphere, is only about 5,500 degrees Celsius. Mysteries Parker Solar Probe was built to solve. For a long time, we thought the surface of the Sun was the hottest part. But the coronal paradox changed everything. The surface is only 500 degrees CO. The corona, over 1,000,000 degrees. Why is the Sun's atmosphere so much hotter than its surface? Another mystery. Solar wind, a stream of charged particles racing across the solar system at up to 3 million kilometers per h, forming the heliosphere. Coronal mass ejections, CMEs, massive explosions that can cause auroras but also disrupt power grids, satellites, and GPS. Parker Solar Probe is the first mission to sample these phenomena right where they start. Eugene Parker, the visionary nobody believed, behind this mission stands a legendary astrophysicist, Eugene Parker. In the 1950s, he proposed that the Sun constantly emits a stream of particles, the solar wind. At the time, his peers rejected the idea and tried to block publication. But satellite data soon confirmed it. In 2018, NASA did something unprecedented. Named a spacecraft after a living person, Eugene Parker himself, who was present to watch the rocket launch carrying his name into space. 3 decades of failure. Why approaching the Sun was so hard. The Sun may seem close, but getting there is one of the hardest engineering challenges ever attempted. Launching from Earth, you're already moving at nearly 30 kilometers per s around the Sun. To get close to the Sun, you actually need to shed energy, slow down relative to the Sun, which is much harder than reaching the outer planets. For decades, there were no materials or technologies capable of surviving the heat and radiation. Only with modern composites, revolutionary autonomy, and smart miniaturization did Parker Solar Probe become possible. How Parker Solar Probe survives. Technology on the edge of science fiction. TPS, thermal protection system, heat shield, 11.4 centimeters thick, carbon composite with foam core, coated with a special white layer to reflect as much solar radiation as possible. The sun-facing side endures up to 1,370 degrees Celsius, but behind it, the spacecraft's instruments are kept at a comfortable 30 degrees Celsius. Active cooling and solar panels. The solar panels are tucked behind the shield. Only narrow tips poke out, actively cooled by circulating fluid. The entire spacecraft is extremely power efficient. It uses less energy than a typical hairdryer. Autonomy and self-healing. For much of its mission, Parker is out of real-time contact with Earth. Signals can take over 8 minutes to arrive. The probe automatically orients its shield, reacts to micrometeoroid hits, and can reboot itself if needed. Minimalism weighs only 685 kilograms. Every component is optimized to minimize exposure and maximize survival in the Sun's hellish environment. Launch and trajectory. When slowing down is harder than speeding up launch. August 12, 2018, from Cape Canaveral, atop a Delta IV Heavy, America's most powerful rocket at the time. But to really get close to the Sun, Parker Solar Probe must use the gravity of Venus 7 times for gravity assists. Each Venus flyby slows the probe's orbital speed relative to the Sun, the opposite of most missions that use gravity assists to speed up. In 2025, Parker will pass just 6.16 million kilometers from the Sun's center. That's only about 9 solar radii, an all-time record, the fastest human-made object in history. In 2021, Parker surpassed 260,000 kilometers per h. In 2025, it will reach over 700,000 kilometers per h, about 0.064% the speed of light. That's 17 trips around Earth every minute. Parker will beat all previous records: Helios 2, New Horizons, Messenger, Solar Orbiter, and every spacecraft ever launched. Scientific instruments. What Parker Solar Probe measures? Fields measures electric and magnetic fields, waves, and turbulence in the corona. Helps explain which waves heat the corona. WISPER, Wide Field Imager for Parker Solar Probe. The first camera to capture the corona and structures close to the Sun. Unique images of solar eruptions, magnetic switchbacks, and dust structures. SWEP measures density, speed, and energy of solar wind particles. Reveals where and how energy differences in the solar wind arise. ISIS detects high-energy particles from solar eruptions. Helps explain why some particles reach Earth in minutes and others take hours. Major discoveries and breakthroughs, magnetic switchbacks. Parker confirmed that the Sun's magnetic field in the corona constantly flips directions in sudden switchbacks. This discovery overturns old models and shows just how dynamic the Sun really is. Solar wind origins. For the first time, Parker sampled the actual regions where solar wind originates. Detected mini eruptions that accelerate solar wind particles invisible from Earth. Dust Ring discovered a dust ring near the Sun, essential for understanding solar system evolution. Coronal holes and CME's direct observation of coronal holes, sources of fast solar wind. Real-time CME data, a revolution in space weather forecasting. Extreme conditions. What Parker Solar Probe must endure? Temperature. Sun-facing shield, 1,370 degrees Celsius. Behind it, just 30 degrees Celsius. Radiation, hundreds of times more intense than near Earth. Micrometeoroids, even tiny dust grains could destroy the probe at these speeds. Magnetic storms, sudden field changes, particle blasts. Autonomy, no room for error, any failure could be fatal, and no human can intervene. Parker Solar Probe versus other solar missions, Helios 2, the old record holder, 43 million kilometers, 252,000 kilometers per h. Solar Orbiter, ESA, similar goals but always farther from the Sun. Messenger Mercury, endured extreme temperatures but nowhere near Parker's solar proximity. Only Parker has truly touched the Sun. Practical impact on Earth space weather forecasting. Faster warnings for geomagnetic storms. Better protection for satellites and power grids. Understanding solar cycles. Improved prediction of high-activity periods, with big implications for technology and society. New materials and automation, heat shields and autonomous systems developed for Parker are already influencing aerospace, nuclear, and robotics engineering. 13. Inspiration, education, and a new era of solar research. Thousands of students worldwide are analyzing Parker's data, creating educational projects, and building mini-probes. The mission is inspiring the next generation of scientists and engineers. Parker Solar Probe features in documentaries, podcasts, even memes. It has become a symbol of human curiosity and the extreme. What's next? The mission's future even closer. By mission's end, Parker will approach within 6.16 million kilometers of the Sun's center. New records. Each orbit sets a new speed and distance record. More discoveries. Data will be analyzed for decades after the mission ends. Risk every close approach could be Parker's last, but the probe has already achieved most of its primary goals. Fun facts and trivia: Parker Solar Probe is the only spacecraft ever named after a living scientist. Communications. A signal from Parker can take more than 8 minutes to reach Earth. Mission cost: $1.5 billion. Modest for a mission of this risk and scale. Every panel, screw, and cable was designed to survive at least 10 close solar passes. Built for hell. If Parker lost its shield, it would melt in seconds. Conclusion: Parker Solar Probe's legacy for humanity. Parker Solar Probe is a testament to human courage, engineering genius, and our willingness to risk everything for knowledge. Thanks to this mission, we'll be able to better predict catastrophic solar storms, protect modern civilization, understand how stars work, and maybe even prepare for life around other suns. Generations to come will remember Parker Solar Probe as the first probe to truly touch the sun.